A spherical cap is the part of a sphere that is generated by the intersection of a plane and a sphere. Given a sphere of radius r, use calculus to show that the curved surface area, a cap, of a spherical cap that subtends 2 theta radians at the centre is given by the formula a cap equals 2 pi r squared into 1 minus cos theta. So first we draw a diagram. Here is a sphere. Here is a spherical cap formed by the intersection of a plane and a sphere. And we want to find the area of the curved surface a cap. So when we use calculus to find an area, we perform an integration, and to do so, we divide the area into thin strips whose shape we can calculate. We add up the area of those strips, and then we work out the area that we get when we let the width of the strips tend to 0. And when we let the width of the strips tend to 0, we are converting a sum into an integral. And graphically, that procedure looks like this. And so we want to divide the curved surface of the cap into thin strips whose area we can calculate. And this problem can be approached in at least 2 different ways, both of which I'm going to demonstrate. So in method 1, we split the cap into strips that are perpendicular to the x-axis. Here is the sphere, with the bottom of the cap at a displacement x0 from the y-axis, and with the radius of the sphere being r. We consider a strip a displacement x from the y-axis, and with a thickness delta x, and this defines a small portion of the cap area. From a more 3D point of view, we have created an approximate frustum of a cone, and we need to calculate the curved surface area, delta A, of that frustum. The slant length of the frustum is delta L, and delta L is a small portion of the perimeter of the cap, i.e. it is this region on the sphere. And the important point to note is that it is nearly straight when delta x is very small. We'll call the larger diameter of the frustum y1 and the smaller diameter y2. Now if we consider a frustum of a cone with smaller diameter little r and larger diameter big R, and with slant length L, then the curved surface area is given by pi into little r plus big R times L. And you can think of A as being given by the average circumference times L. And so from that result we have that delta A is roughly pi into y1 plus y2 times delta L. Now we find expressions for y1 and y2 in terms of x. This is straightforward. From Pythagoras' theorem we see that y1 is the square root of r squared minus x squared, and that y2 is the square root of r squared minus x plus delta x all squared. And so delta A, which is pi into y1 plus y2 times delta L, becomes this expression. But to continue, we need to find delta L in terms of x as well. So here is a picture of the strip of the spherical cap, and here is delta L, and we consider this triangle where delta L subtends delta theta at the centre. Now this is an equilateral triangle, and we call the two angles at the base phi. So we have that delta theta plus 2 phi equals pi, so that phi equals pi by 2 plus delta theta over 2. And as delta x tends to 0, so does delta L and so does delta theta. And so phi tends to pi by 2 as delta x tends to 0, as we can see by considering this equation. So if we zoom in on this portion of the picture, then when delta x is very small, it looks like this, where the angle phi has become 90 degrees. So if we indicate delta x, like so, with the angle between delta L and delta x being alpha, then we see that delta x equals delta L cos alpha, so that delta L equals delta x over cos alpha. Now we can see that this angle is alpha, and by looking at the diagram in the middle, that implies that cos alpha equals y1 over r, so that 1 over cos alpha equals r over y1. And we see that y1 equals the square root of r squared minus x squared, so the delta L equals r over the square root of r squared minus x squared times delta x. And now we can get an expression for delta A purely in terms of x as follows. So now we sum up the delta A strips, and we convert that sum into a definite integral by taking the limit as delta x tends to 0. And we can represent that as follows. Now we know that delta A is given by this expression, but what happens to it as delta x tends to 0? Well, first, this delta x is replaced by dx, and this dx is the dx of the integral, and it tells us against which variable we are integrating. Now, this is the only other expression with a delta x. What happens to that as delta x tends to 0? Well, as delta x tends to 0, x plus delta x tends to x, so that the square root of r squared minus x plus delta x all squared tends to the square root of r squared minus x squared, and so the expression in question tends to the square root of r squared minus x squared over the square root of r squared minus x squared, which equals 1. And so the required f of x becomes pi r into 1 plus 1, which equals 2 pi r, which is a remarkably simple result. And now we need to find the limits for the integral, which will be in terms of x. So here we have a picture of the cap, which extends from an x displacement of x0 to an x displacement of r. And so the lower limit is x0 and the upper limit is r. And to see that, you can visualize a thin strip of width delta x sweeping along the x-axis from x0 to r. And so we have that a cap equals the integral from x0 to r of 2 pi r dx, which evaluates to be 2 pi r into r minus x0. Now from the diagram we see that cos theta equals x0 over r, and so we rewrite the result of our integral as 2 pi r squared into 1 minus x0 over r, which equals 2 pi r squared into 1 minus cos theta as required. Now we can note that when theta equals pi, the cap will cover the whole of the sphere, so its area should be 4 pi r squared. And we can see that when theta equals pi, a cap does indeed evaluate to be 4 pi r squared, as expected. In method 2, we break the cap up into sectors defined by an angle, and the variable of integration is alpha. So here is the cap, and we consider a sector of radius r and with arc length delta s, which subtends an angle delta alpha at the centre. And so we have that delta s equals r delta alpha. The sector is located at some arbitrary angle alpha from the x-axis. Now this sector defines a strip of area delta A where this dimension is y and where y equals r sine alpha. Now in 3D the thin strip looks like this, with a radius approximately equal to y and whose surface area is delta A. Now we have that delta A is approximately equal to the circumference of the strip times delta S, which is approximately equal to 2 pi y delta S, which equals 2 pi r sine alpha r delta alpha, or 2 pi r squared sine alpha delta alpha. And so a cap is roughly equal to the sum of the delta a's, which equals the sum of 2 pi r squared sine alpha delta alpha. And we can turn the sum into an integral by letting delta alpha tend to 0. And we note that alpha must vary from 0 to theta radians to ensure that the strip covers the required cap area. And so we have that a cap equals the integral from 0 to theta of 2 pi r squared sine alpha d alpha, which evaluates as follows to 2 pi r squared into 1 minus cos theta as required.